Hello all, I'm back with another video, and this is Unit 6 from January 2026, and it is the most recent one. And just like with all the other units, there is also a Unit 6A, so a second version of the same paper, which is different from this one, which I plan to upload soon. I'm sorry for not uploading for some days now. I was busy with other stuff. Let's dive in because I have something else to do later. So let's start with question 1. Two students, A and B, investigated the projectile motion of a sphere using the apparatus shown. And I mean, you can imagine what's going on there. You have this ball flying off the rails there and then falling somewhere in the sand tray they have under the ball. Okay. Question A. Student A placed the sphere on the track at the initial position. He released the sphere and it moved down the track. The sphere then traveled through the air to its final position in the sand tray. The surface of the sand was horizontal. He placed the meter rule on the ground as near to the sand tray as possible. He measured the horizontal distance x between the end of the track and the final position of the sphere. Describe a method to determine an accurate value for x, and that's x. I mean, I circled it over there. So, so I guess the best way is to use a plumb line. Okay, it's that bob that hangs from a string and it points towards the center of gravity. Okay, so use a plumb line to accurately find the end of the track. Okay, measure to the center of the sphere. That's the other thing you need to do. Use a set square. Use a set square to measure the scale perpendicularly. And finally, take many measurements as usual. So take many measurements, usually 3 to 5, and take the average. Okay, so it's the usual stuff they ask in these types of questions. And I forgot to mention that Unit 6 takes an hour and 20 minutes, as you can see there. So, for example, this question awards 3 marks. So it should take about 3 minutes. I mean, I say these things in all my videos. So, yeah. So, for example, question 1 awards 9 marks. So it should take you about 9 minutes to solve it, just to stay on time. So, question B. Student A repeated the experiment using 5 identical spheres and measured x for each sphere. Student B used the same apparatus to determine another set of values for x. The diagrams below show the final positions of the spheres for both students. And this is a view from above, not to scale. And you see that for student A, there is a cluster that is well concentrated around a value, whereas student B's results are more scattered. So, question I, explain why the final position of the spheres varied for the repeated experiments. So, one reason can be that spheres have different velocities as they leave the end of the tracks. Okay, that can be one reason. Let me use a clean page. So this is B I. Okay. The second reason is that maybe they were released from different heights. Okay. And the third reason is that maybe a force was used. So maybe a force was used. So what I'm trying to say is that let me go to the apparatus. So let's say that this is the sphere. So maybe a student, instead of placing the sphere at the top of the stand, maybe he or she put it there, or maybe they accidentally pushed the sphere as it was going down. So the velocity when it reached the bottom of the track was different. Okay, so that's the idea of what could possibly have happened. So question 2. Student A made the following statement: my values of X are more precise than student B's values, so they are more accurate. Explain whether student A's statement is valid. So for student A, okay, the values have a smaller range. And therefore, student A's values are more precise. Okay, this is what precision means. So this is what precise means. If we look at the picture here, all the values are concentrated. So this is what precision means. Like everything is not far from everything. Every measurement is not very different from other measurements. Okay. So, but student B's values are not precise. But there is, but when we talk about accuracy, accurate means close to the true value. In this case, we don't know what the true value is. So let's write this down. So no true value is known. Okay. Therefore, student A is wrong about accuracy. Okay, and this is question 1. I mean, I think we covered everything. We can move on. So, question 2. A student used the apparatus shown to investigate the rotational oscillations of a mass suspended from a wire. The wire remained vertical while the mass was rotating. And you can see what's going on here. So basically, you twist the mass a few times around, and then you let it go, and then the system rotates and undergoes rotational oscillations. Okay, this is something you don't learn at the A level, but it's easy to understand, or even experiment with it if you want. So the student rotated the mass through a small angular displacement. She released the mass. The mass made the rotational oscillations around the vertical line. The student determined the time period T of the oscillations with a stopwatch. The student used the meter rule to measure the length L. For this investigation, the relationship between T and L is given by that formula over there, 2 pi and then the square root of r squared times L over 5k, where r is the radius of the mass and k is a constant. Devise a method the student could use to determine a value for k. Your method should include the use of a suitable graph. Okay, so, and this is a 6-mark question, so we have to provide about 6 arguments or 6 points for, 6 sentences to describe the experiment. So first of all, you have to measure, she has to measure the diameter of the mass using vernier calipers, and then find r, the radius. Okay, repeat the diameter measurement at different orientations and calculate the mean. And again, for different orientations, we mean that, okay, this is a circle, right? Actually, I can make a better circle now. So let's do this. Okay, so that's a circle. So you can measure the diameter along this direction and then this direction and then along this direction and then calculate the average. Okay, so this is what we mean by different orientation, because maybe there are slight deviations from the circle around different orientations, so you average those out. Okay. You can also place a marker at the equilibrium position to make timing easier. What do you mean by that? If, for example, the position of equilibrium is here, you can put an arrow, like we can put a stand with some marker at the point where the equilibrium is, so that you can time your oscillations and make more accurate measurements of the period. Okay. Now, the other thing you can do is to measure the time for several oscillations, and usually 5 to 10 is a good number. Okay, and then divide by the number of oscillations. What am I doing today? Okay, by the number of oscillations to find t. Okay, and the last thing is to repeat, not the last, second to last. So repeat for at least 5 values of the wire length Okay, and if you have those 5 values, you can plot t squared versus L, because if we go back and take this formula, we see that t squared is 4 pi squared r squared over 5k times L. So this gradient, let me write it in red. So the gradient is 4 pi squared r squared over 5k. So with the radius known, you can calculate that constant k in the denominator by just calculating the gradient. Okay, and this is a full answer for question 6. So in general, you see that these kind of questions repeat themselves over and over again in different contexts, but the general rules are that if you have to measure diameter, you use different orientations. And if you need to measure oscillations, you usually time 5 to 10 oscillations and then you divide. Another thing you can do is, what else? I mean, when you plot, you usually plot straight lines, and then you, from the gradient, you can calculate something unknown, etc. So let's move on to question 3. Okay, the photograph shows an anemometer. Anemos, by the way, in Greek means wind. Okay, so an anemometer is an instrument used to measure wind speed. Okay, as wind speed increases, the airflow past the cups also increases. When air flows past the cups and the axle rotate. A student investigated the output from an anemometer using the apparatus shown. She used the desk fan to move the cups at a steady speed. So this is the anemometer and it rotates. And there are some magnets here, and you have a coil rotating, so you have an EMF generated. Okay, and you use a desk fan to create wind. All right, so let me raise those. And we get this nice graph over there. Okay, in the screen. The axle is attached to a coil inside the generator. As the axle rotates, the coil rotates in the magnetic field between the magnets. The coil output was displayed on the oscilloscope screen as shown below. Okay, question I. The horizontal scale was set to 200 milliseconds per division. Determine the linear velocity of the cups. The distance from axle to the center of the cup is 18 centimeters, so you can immediately write that the radius is 0.18 meters. And then we need to find the period, okay? So you can use any two peaks you want, so you can measure from there to there, or from there to there, etc. Or you can use valleys, or you can use these points, these points, etc. So in my case, I used this peak and this peak. So if you go down, you see that you have 1, 2, 3, and then about 3.8 divisions. Okay, so the period is gonna be, because one period is peak to peak, right, or valley to valley, etc. So peak to peak is 3.8 divisions times 200 milliseconds yields 760 milliseconds, which you can write as 0.76 seconds. And then the velocity is omega times r, right? So 2 pi over the period times r. So 2 pi over 0.76 times 0.18, and that's 1.49 meters per second. Okay. Question 2. The student changed the setting on the desk fan to increase the speed of the airflow. Describe how the output shown on the oscilloscope changes as the airflow past the cups increases. So if we increase the speed, we will reduce the period, so the peaks will come closer together, okay, and more EMF will be generated, okay, which means that the peaks will get higher. So let's write those two things down. So peaks will come closer together, since the generator speeds faster, so it produces more waves. And the second observation is that the amplitude gets bigger as the generator is spinning faster. So a larger voltage, a larger voltage is produced. And recall that the EMF is given by minus delta phi over delta t. Therefore, this thing is going to be proportional. Since phi is, we can actually expand it a little bit more. So this is minus delta delta B A over delta t. The magnetic field is constant since we use a permanent magnet, right? So it comes out of the derivative. So it's B delta A over delta T. And that delta A over delta T is going to be proportional to omega. And the reason is that the surface that cuts through the magnetic field lines rotates, okay? Therefore, sometimes it's going to be cutting through the magnetic field lines, and sometimes, within a period, it's at some point, the surface is going to be parallel to the magnetic field lines, okay? So in general, the EMF is going to be proportional to omega. Therefore, if we spin faster, we will see something like this. So larger peaks and faster period, okay? Something like that. All right. B, how do you pronounce that? Beaufort wind force scale, I guess, is a numerical scale used to estimate wind speed from the observed effects of the wind. It is suggested that mean wind speed V is related to the Beaufort scale number B as V equals to PB to the Z, where P and Z are constants. Explain how a graph of log V against log B could be used to determine the values of P and Z. So since V is PB to the Z, then log of V is log of P plus Z log B. Okay, so this is of the form Y equals a constant plus mx, and the gradient, which is equal to m, is going to be Z, and the y-intercept is going to be log of P. Okay, and that's a way to calculate P and Z from a graph. Okay, question 2. The table shows values of mean wind speeds V and their Beaufort scale number B. Plot a graph of log V against log B on the grid opposite. Use the additional columns in the table to record your process data. So as I do usually, I'm going to fill in one value and then I'm going to speed up the video for you. So we have, in one column, we have log of V and then log of B. Okay. To be totally correct, actually, you have to write log of V over meters per second. So maybe we can write meters seconds to the -1, but it's okay, it's a technicality. Okay, so the log of 2.45, you can use your calculator. Use the log, not the ln, the log, okay? So the log is 0.39, and the log of 2 is 0.3, and then you will see the values in a moment. Okay, so one thing to do before plotting is to find the range of these values. So the range of log V is from about 0.3 to about 1.1. So your scale should be it should come in increments of 0.1, so 0.3, 0.4, 0.5. So it's easier for you to find points. And then the range of log of B is from 0.3 to 0.8. So you can use increments of 0.1 as well. So 0.3, 0.4, 0.5, etc. All right. So let's start constructing this graph. Let me use green so it's visible. Okay. So this is the y-axis, the x-axis. So here we have log of V and log of B. And I'm going to start with the first point and then I'm going to speed up the video. So the first pair of values is log B is 0.3. I forgot to put the scales. Excuse me. So, okay, 0.3 is the first one, 0.4, 0.5, 0.6. So I'm using these large squares because there is enough space. Okay, 0.7, 0.8, 0.9, 1, and then 1.1. And then for log b, we can start again from 0.2. So let's make this 0.3. So it's 0.4, 0.5, 0.6, 0.7, and 0.8. And I don't remember mentioning it in other videos, but you can start with your scale from something that is not zero, okay? But there is one problem with that, and we will see it in a moment. So anyway, the first pair of values is log b is 0.3, and log v is 0.39, which is this point over there. And then I will speed up the video, okay? All right, so this is the graph. It kind of looks beautiful, okay, I think. So let's connect the points with orange or maybe blue. Okay, let's do blue. So we have to pass a best fit line. So yeah, that looks good. Okay. And again, the trick is, let me think. So the trick is to make a line that passes through all points, and then there must be as many points above the line as there are below the line. But okay, this is good enough. So I hope this is clear. Let's move on to question 3. Determine the value of z from the graph. So z is the gradient. Okay, and you can use any 2 points you want from this best fit line. And the points I used, I actually used them from the table. Okay, so I'm using this pair of values. So I'm using this, and what else am I using? And this. Okay. So, but you don't have to do this. You can use, for example, this point and then this point. Okay, this is clear enough. So you should find approximately the same result. So these 2 points, for example. Okay, so you have to measure this distance and then divide by this distance. Okay, so in my case, I used 1.09 minus 0.39. And then in the denominator, we have 0.78 minus 0.3, which yields 1.46. Okay, let's move on to question 4. Determine the value of of p from the graph. So now we are encountering the problem I was talking about earlier, and I said that when your graph does not start from 0, 0, it creates a mess with the y-intercept, so it's not safe to use the y-intercept. So the way we'll do it is to recall that the equation governing the line is log v equals to log p plus z log b. Okay, now z is known, so we can use a pair of values. So use a pair of values and plug into the equation to find the unknown. Okay, and let me use a clean page and you will see what I mean. So for example, if we use the pair 0.39 and then 0.3. Okay, and if we plug into the equation, we have 0.39 equals to log p plus 1.46 times 0.3. Okay, which means that log of p is minus 0.048. Okay, which means that p is 10 to the minus 0.048, which yields 0.9. Okay, I hope this makes sense. We will move on. When the Beaufort scale number is 10, weather conditions are defined as a storm. Determine the mean wind speed v for a storm. Okay, so now we will use the equation itself, and I am talking about this equation over there. Okay, so since v is p times b to the z, if we plug in the numbers for P and Z that we found, and then the B they give us, we can calculate the wind speed. So P is 0.9, B is 10, Z is 1.46, which yields 25.82 meters per second. And this was question 3. That worth 22 marks. That's a lot, okay? But I think it's straightforward. Like it kind of solves itself if you know how to do basic logs and stuff like that. All right, let's move on. Question 4. A student made measurements on a metal cone as shown. So we see the cone there. The base of the cone is circular. The volume V of the cone is given by V equals to pi d squared h over 12, where d is the diameter of the base and h is the height of the cone. The student used a meter rule to measure h. Describe a technique he should use to determine an accurate value for h. Okay, the way I thought about this is that you can define, let's call this side of the cone L, okay? So this is L, and notice that this is a right triangle, okay? So that's a right triangle, and H is one of the sides, and the other side is D over 2, okay? So you can say that you can measure L, take 5 measurements, an average, and then similarly measure D in the same way, meaning that you measure it for 5 times an average, and then use Pythagoras. So d squared over 4 plus plus h squared is equal to L squared. So h is simply the square root of L squared minus d squared over 4. That's the answer. That's how you can calculate h. All right. B. The student recorded the following measurements for D, and we see 4 measurements, okay? He determined a mean value for H as 2.93 plus or minus 0.02 centimeters. The student used a digital mass balance to measure the mass of the metal cone as 60.5 grams. Show that the density rho of the metal is about 8.9 grams per cubic centimeter. Okay, so the first step is to find the average value for D. So 29.82 plus 29.84 plus 29.88 plus 29.87 over 4 yields 29.85 millimeters, and we can convert to centimeters since we will need that. So 2.99 centimeters. Okay, the half range, which we will need later, half range is 29.88. That's the one extreme, and the lowest extreme is 29.82 over 2 yields 0.03 millimeters. Okay, and we have the age, we have the mass, so I'm going to use a clean page to calculate the density. So rho is just m over v, right? The volume for the cone is pi times d squared, 2.99 squared times the height, 2.93 over 12, which yields 6.86 cubic centimeters. Okay, and then rho is m over v, So 60.5 over 6.86, and this is grams per cubic centimeter, and this yields 8.82 grams per cubic centimeter, which is close to what they ask, 8.9, okay? Part 2, show that the percentage uncertainty in rho is about 1%. Okay, so this is a little bit more complicated, but not too complicated. So rho is m over v. I have a video about uncertainties, by the way, you should watch. So when we divide physical quantities, we add their percentage uncertainties. So the percentage uncertainty in rho is equal to the percentage uncertainty in m plus the percentage uncertainty in v. Now for v, you see that we are multiplying physical quantities. We are actually multiplying v is proportional to d squared times h, right? So when we multiply, we again add percentage uncertainties, and whenever we take the power of a physical quantity, we multiply the percentage uncertainty by that power. So what I mean is that let's keep expanding this. So this is the percentage uncertainty in mass plus the percentage uncertainty, the percentage uncertainty in v is equal to the percentage uncertainty in d squared plus the percentage uncertainty in h. Okay, and now the story is that the constants, so in this case we have pi over 12, right? That doesn't count when you take percentage uncertainties, okay? If it was absolute uncertainties, you count for that. But for percentage uncertainties, you don't, okay? So we have one more step. So this is equal to the percentage uncertainty in m plus the percentage plus 2 times the percentage uncertainty in d, which is what I said about the percentage uncertainty of a physical quantity to some power, plus the percentage uncertainty in h. Okay, and now this is equal, okay, the percentage uncertainty in mass. So the mass is 60.5 grams, meaning that this instrument can count down to 0.1 grams. So the absolute uncertainty in the measurement of this instrument is half the smallest deviation of the instrument, so 0.05 grams. Okay, so the percentage uncertainty in mass is 0.05 over 60.5 times 100, and then plus 2 times the percentage uncertainty in D. So the absolute uncertainty in D is 0.03, right? So we multiply with 0.03, we divide by the value itself, which is 29.85 times 100, and then plus 0.02 is the absolute uncertainty in the height, 2.93 is the height times 100. Value is, the final result is 0.96%, which is about 1%. Okay. And we are left with the last question, 3. In a textbook, so this is a typo. In a textbook, in a textbook, it is stated would be the correct one. Okay, so that's a typo. That the density of brass is 8.53 grams per cubic centimeter. Deduce whether the cone could be made from brass. Okay, so the value we found is rho is 8.82 grams per cubic centimeter. If we multiply with the percentage uncertainty, we can find the absolute uncertainty. So the absolute uncertainty in rho is equal to the percentage uncertainty in rho times rho. So 0.96 times 8.82 yields 0.08 grams per cubic centimeter. So rho is 8.82 plus or minus 0.08 grams per cubic centimeters. So the lowest value is 8.82 minus 0.08, which is 8.74 grams per cubic centimeter. which is larger than 8.53 grams per cubic centimeters. So not brass. All right. And this was Unit 6, the most recent one from 2026. I hope these videos are useful. By the way, I noticed that, for example, Unit 4 papers get way more views than, say, Unit 3 papers or Unit 6 papers. So usually the most viewed papers are Unit 4 and Unit 5. So if anyone is watching this, please let me know which papers are most needed. Okay, so I put more videos from that unit out. So something like that. Thank you to those who are subscribing and following and commenting. So I have one more paper, and that is Unit 5, the second version from 2026. So I hopefully will upload that soon. So anyway, thank you guys. Bye.